Ma'am, I'll start. Ma'am.
Yes, sir. Good evening, sir. You can start now, sir.
Good evening. Today we'll not be learning the test papers. We will learn some of the synopsis of some of the chapters, right? Like electrochemistry and chemical kinetics, wherein a lot of numericals are there. A lot of formulas and numericals to be learned. Based on that, we will learn some of the concepts, one or two questions, and also we will learn the formulas which you should remember. The first one is electrochemistry. The first chapter is electrochemistry. The name itself says electron chemistry. It is concerned with electricity and chemical reactions. We all know that electrochemistry deals with the study of interconversion of energies. Interconversion of energies. Not only interconversion of energies, but also we study in this chapter behavior of electrolytes. Now, when we say interconversion of energies, now one is a chemical energy is converted to electrical energy. The cell which converts chemical energy into electrical energy is called as electrochemical cell. An example for electrochemical cell, a dry cell. For torch, we use dry cell. Likewise, mobile batteries. There's lithium-ion battery. It is called as mobile batteries. Right? Acid batteries. Acid batteries, when you say lead storage battery, PB, lead storage battery, car batteries, lead storage batteries. All these are examples for a cell in which chemical energy is converted into electrical energy. Likewise, electrical energy can also be converted into chemical energy. A cell which converts electrical energy into chemical energy is called as electrolytic cell. Normally, this electrolytic cell is used in metallurgical processes. Metallurgical processes like Nelson's cell, Dow's cell. All these are examples for electrolytic cell. So chemical energy can be converted into electrical energy, or electrical energy can be converted into chemical energy. In electrochemistry, the reaction taking place is always a redox reaction. Always a redox reaction. Now, when we say it's a redox reaction, it is oxidation and reduction will be taking place simultaneously. Therefore, it is called as a redox reaction. So redox reaction means a reaction in which oxidation and reduction takes place simultaneously is called as a redox reaction. Now, what is this oxidation and what is this reduction here? We should understand oxidation means loss of electrons. Oxidation means loss of electrons. And reduction means gain of electron. So in electrochemistry, the reaction taking place is redox. Oxidation and reduction will take place simultaneously. Oxidation will always take place at anode and reduction will take place at cathode. Anode is a positive electrode represented by negative sign. Anode is a positive electrode represented by negative sign. Cathode is a negative electrode represented by positive sign. Remember, the sign conventions are different here. So negative electrode is represented positive and positive electrode is represented negative. So what happens? Just give me some time. One minute. Sorry. Now, reduction it's happening at a cathode, and cathode is a negative electrode, and it's represented by positive sign. Now, anode, oxidation takes place at anode. What we mean by oxidation? What we mean by oxidation? Oh, can you see the board? Can you see the screen? Students, can you see the screen? Tanushree, can you see the screen? Ma'am? Hello? Ma'am? Okay. Something went wrong. Something went wrong. All right. Something went wrong. So, and my pen is also, this is also not working. Why is not working? Yeah. Now, as I was telling, the reaction taking place is a redox reaction. Oxidation and reduction will take place at electrodes. Oxidation will take place at anode. Anode is a positive electrode represented by negative sign. Reduction takes place at cathode, represented by a positive sign. Now, oxidation means loss of electrons, and reduction means gain of electrons. So at anode, electrons will be lost, and at cathode, electrons will be gained. So both oxidation and reduction takes place simultaneously. Therefore, it is called as a redox reaction. Now, in order to understand this, we need to talk about something called as an electrode. This electrode means metal in contact or metal dipped in its own ions. Metal dipped in its own ions is called as an electrode. No, I don't know how to allow it. I don't know. You have to talk, call Stella ma'am. She will guide you. Ask to call Stella ma'am. Now, metal dipped in its own ions is called as an electrode. Now, for an example, if we have a metal like this, zinc rod in contact with zinc solution, zinc ions, zinc sulfate solution, it is Zn2+. It is called as a zinc electrode. Now, if we take copper rod, and this copper rod is in contact with copper ions, it is called as copper electrode. So metal dipped in its own ions will be called as an electrode. Now, these electrodes are connected externally by means of an insulated wire through a voltmeter. This voltmeter is used to measure voltage. And these are connected internally by means of a salt bridge. This is the construction of Daniell cell. This is the construction of Daniell cell. Now, each electrode will be called as a half cell. Each electrode is called as a half cell. So two half cells will give one complete cell. Now, it's an example for an electrochemical cell. Name of the cell, what has been written here or explained here, is Daniell cell. So Daniell cell consists of zinc electrode and copper electrode connected externally through a wire using a voltmeter, connected internally by means of a salt bridge. Now, whatever electrode is replaced on the left-hand side is anode. Whatever is placed on the left-hand side will be anode. It is called sign convention. Whatever is placed on the right-hand side will be called as cathode. Cathode is a negative electrode represented by positive sign. I clearly told you the sign convention. Now, at anode, always oxidation takes place. So what happens is zinc will dissolve into solution from zinc ions and electrons. Now, these electrons which are given here, these electrons will move towards copper electrode. At cathode is a negative electrode, represented positive sign. Reduction has to take place. Reduction means gain of electron. So these electrons which move towards copper, these copper ions will accept electrons and get reduced to copper. So loss of electron is called as oxidation. Oxidation always takes place at anode. Gain of electron is called as reduction. Reduction always takes place at cathode. So when you add these two equations, we get zinc plus Cu2 plus. These electrons will get cancelled, giving you Zn2 plus at copper. This is the overall reaction. So this loss of electron at anode, gain of electron at cathode is a change in chemical energy. This change in chemical energy appears as current. So current flows from cathode to anode. Current will flow from cathode to anode. Now this is with respect to the electrochemical cell oxidation reduction. Now this electrodes, each electrode, metal dipped in its own ions is called as an electrode. As I told, metal in contact with metal ions will be called as an electrode. So when metal comes into contact with metal ion at equilibrium, an electrode potential is developed. That electrode potential developed is called as the potential developed is called as electrode potential. So metal, when it is in contact with its ions, a potential will be developed, and that potential is called as electrode potential, represented as E. Now, if the electrode potential is measured at standard conditions, 298 Kelvin and 1 molar concentration, it is called a standard electrode potential. It's represented as E0 value. E0 is standard electrode potential. Now, quickly, we'll have to learn some of the formulas to work out some of the problems. Now, this is with respect to the introduction of electrochemistry. What is electrode potential? We learned, right? That electrode potential is normally, if we measure the electrode potential in terms of reduction, it will be called a standard reduction potential. If it is with respect to oxidation, it will be called a standard oxidation potential. Now, coming to the EMF of the cell, how do we measure the EMF of the cell? Now, EMF of the cell can be measured by electrode potential of the cathode minus electrode potential at the anode. Electrode potential of the cathode minus electrode potential of the anode. So EMF of the cell, E cell, is calculated by the formula. E naught of cell can be calculated by the formula E naught of cathode minus E naught of anode. Now, in the previous topic, I was talking about Daniel cell. In order to construct Daniel cell, we need a zinc electrode, and also we need copper electrode. The electrode potential of zinc is minus 0.76 volt, and of copper is plus 0.34. So what is the EMF of the Daniel cell? The EMF of the Daniel cell is E naught of copper minus E naught of zinc. So that is plus 0.34 minus of minus 0.76. So it will be plus 1.1. Now remember, this is an important point which you should remember. Now they may give you different electrode, electrode X and electrode Y. They will give you this, these are electrodes, and they'll give you electrode potential. They'll give you electrode potential. This electrode potential may be 2.5, and this will be 1.5 volts. It's in volts. It's only for illustration. Now, how do we know which is undergoing reduction and which is undergoing oxidation? Now, always remember, larger the potential will undergo reduction, and smaller the potential will undergo oxidation. Now, you can observe here also minus 0.76 and it's plus 0.34. Larger will undergo reduction. Reduction normally happens at cathode. So we can write this also E naught of reduction minus E naught of the electrodes undergoing oxidation. Smaller the value for electrode potential, it will undergo oxidation. Smaller the value of oxidation potential, it will undergo oxidation. Do not forget this. In some of the questions, they will give you different electrodes, and you should be in a position to identify. Now, for an example, if you take a aluminum, you calculate the EMF of a cell formed by combination of aluminum and iron electrode. Calculate the EMF of the cell formed by combination of aluminum and iron electrodes. They've given E naught of aluminum is minus 1.66 volt, and E naught of iron is minus 0.44 volt. Now both are in negative sign. See the potential, both are negative. But you should remember, this is lower value compared to this. So 0.44 is higher than 1.66, minus 1.66. Therefore, what will be the EMF of the cell? EMF of the cell will be equal to E cathode minus E anode. So larger the value which undergoes, or larger the value, that will be cathode. So larger value is higher values here, iron minus 0.44 minus of minus 1.66 volts. So it will be minus 0.44 plus 1.66. So you'll get 1.22 volts. So you should remember to identify the electrode which is undergoing oxidation and reduction. Larger the value will undergo reduction, and lesser the value of the electrode potential will undergo oxidation. Now, this is one of the simple formula which we learn. We will learn few more formulas like this, and one or two questions also simultaneously we will try to learn. Next is electrolytes. Electrolytes, you know, which conducts electricity will be called as an electrolyte. And in that we have strong electrolyte, weak electrolyte, non-electrolytes, all that. I'm not going to discuss those topics. So chemical substances which conducts electricity in solution state, fused state, or in molten state will be called as an electrolyte. All ionic compounds, all acids, all bases, all the salts are electrolytes. Now, chemical substances which do not conduct electricity will be called as a non-electrolyte. Generally, covalent compounds are non-electrolyte. Now, coming to electrolytes, again, we have two types. One is strong electrolyte and weak electrolyte. Strong electrolyte undergoes complete ionization, even at minimum dilution. Therefore, they call it strong electrolytes. Now, weak electrolyte, when we say the weak electrolyte undergoes partial dissociation, even at maximum dilution. So, examples. Now, Daniel's cell representation. Daniel's cell representation. How do we represent a Daniel cell? I forgot to tell you, we know that zinc electrode is taken as anode and copper electrode is taken as cathode. And I told you zinc will undergo oxidation, Zn2 plus to 2 electrons. And copper 2 plus will undergo reduction to form copper. Copper electrode will undergo reduction, zinc electrode undergoes oxidation. How do we represent Daniel cell? Any electrochemical cell for that matter is represented in this fashion. Anode is represented on the left-hand side, cathode is represented on the right-hand side. Now here, in case of anode, zinc is undergoing oxidation from Zn0 to Zn2 plus. So it will be Zn to Zn2 plus. This parallel line indicates a salt bridge. And you can see copper undergoes reduction from Cu2 plus to C. So the single line indicates interface between the metal and the metal ions. Here also single line indicates interface between the metal and the metal ions. Now you have to mention the concentration. If you mention it 1 molar, 0.1 molar, whichever it is, you can mention the concentration, whatever concentration is used. So this is with respect to the cell representation, electrochemical cell representation. Now, one minute. Now, coming to the next part of the topic, it is you know as salt bridge. What's the importance of salt bridge? Now, you should remember, salt bridge is a bent tube. Salt bridge is a bent tube in which saturated solution of potassium chloride or ammonium chloride or potassium nitrate is filled. Glass tube in which we have saturated solution of potassium chloride, ammonium chloride, or potassium chloride. Because potassium nitrate. Because this will dissociate to form K plus and Cl minus. This will dissociate to form ammonium ion and chloride ion. This will dissociate to form potassium ion and NO3 minus. The speed at which these ions move will be almost the same. K plus will move at the same speed as Cl minus. NH4 plus will move same speed as Cl minus. K plus will move at the same speed of NO3 minus. Therefore, these three components are used in the salt bridge. Along with this, to hold this, they use a gel called as agar-agar jelly. Agar-agar jelly. Otherwise, if it's only a solution, the solution will come out of it. Therefore, a jelly is used to keep this in a salt bridge, a bent glass tube, which is containing saturated solution of potassium chloride or ammonium chloride or potassium nitrate. What's the importance of salt bridge? The salt bridge importance is, first one is to maintain electroneutrality. To maintain electroneutrality. Second one, to avoid liquid junction. So if salt bridge is not present in the electrochemical series, the electrochemical cell, the potential will drop to 0. Therefore, we need to have an electrochemical salt bridge. So if salt bridge is not there, the potential will drop to 0. Now, if we are using any other components excepting KCl, ammonium chloride, potassium nitrate, excepting these three, if we use any other, for an example, if we use HCl, assume that we are using HCl. H plus will move much faster than Cl minus. So since the ionic mobilities of positive and negative ion are more, what happens is the potential will start fluctuating. Fluctuating. We will not have a constant potential. So therefore, we cannot use any other salt, excepting these three. We cannot use any other salt because the potential will start fluctuating. Therefore, we need to use only these KCl, ammonium chloride, and ammonium potassium nitrate in the salt bridge. Now, coming to standard electrodes, we have two types of standard electrodes. One is primary standard, the other one is secondary standard. Now, primary standard electrodes, we have hydrogen. Only hydrogen electrode is a primary standard electrode. This primary standard electrodes, why it is primary? Because firstly, why need to have a standard reference? Primary is not standard, but reference electrode. Primary reference electrodes. These electrodes are used to find the potential of others. So primary reference electrodes. Example for primary reference electrodes is standard hydrogen electrode, SHE. The standard hydrogen electrode, SHE. So conventionally, the potential is taken as E naught of hydrogen electrode is taken as 0 volts. It is not 0 volts. It is one of the demerit. We are not learning the construction of hydrogen electrode, right? It's not for a regular class. It is for a electrode potential of hydrogen electrode is conventionally taken as 0. And now, what are the limitations of hydrogen electrode? Hydrogen electrode, it's very difficult to pass the pressure of hydrogen gas at 1 atmosphere for a long time. In order to prepare standard hydrogen electrode, we need to pass hydrogen gas. You know all that. And to pass that hydrogen gas for a long time at constant pressure, it is not possible because the temperature in the atmosphere is fluctuating. Therefore, it's not possible. And also, to maintain the concentration of HCl, to maintain the concentration of the acid in the solution, is also difficult. Some of the hydrogen gas, what we pass, it may dissolve. Therefore, it is difficult to have hydrogen electrode. And hydrogen gas is extremely pure, must be extremely pure. It should not contain even dust. If it contains dust, it will poison the platinum metal. So therefore, hydrogen electrode cannot be used. And hydrogen electrode cannot be used in the presence of a reducing agent, oxidizing agent. It cannot be used in the presence of oxidizing agent. Now, how do we Nernst equation? Now, these are the formulas which you have to remember. One is Nernst equation. Nernst equation. For single electrode potential, for single electrode, E is calculated by the formula. Electrode potential is calculated by the formula E naught plus 0.0591 divided by N log of Mn plus. Now, one example I'll give you for this particular formula. See, this is the formula to calculate the single electrode potential. That means only one electrode will be there. So electrochemical cells are made up of 2 electrodes, I told you in the beginning. Now, in order to calculate the potential of a particular electrode, single electrode, the Nernst equation is E is equal to E naught plus 2.303 RT by NF log Mn plus, or at 25 degrees Celsius, it is E naught plus 0.0591 by N log Mn plus. Now, what is the half cell potential? What is the half cell potential of zinc in zinc sulfate solution? Here the concentration is 0.01 molar for zinc sulfate at 25 degrees Celsius. And they've given you standard reduction potential of zinc electrode to be minus 0.76 volts. So what will be E now? E will be equal to, this is the formula, 25 degrees Celsius is 298 Kelvin. When you substitute, you will get this value. E naught plus 0.0591 divided by n log of mn plus. That will be equal to minus 0.76 plus of 0.0591 divided by n value. It is zinc electrode. It is Zn0 to Zn2 plus. So it will be 2 log of Mn plus concentration. That's metal ion concentration, zinc concentration step 0.01. So this can be written as minus 0.76 plus of 0.0591 divided by 2 log of 10 to the power minus 2. So on simplification, the value you will get is 0.819 volts. So this is the formula to calculate the single electrode potential. Now, if you have to calculate the EMF of the cell, what is the Nernst equation? That we are going to learn. A cell is made up of an electrochemical cell is made up of two half cells. So how do we calculate the EMF of an electrochemical cell? In order to calculate the EMF of the electrochemical cell, the Nernst equation is given by Nernst equations. Nernst equation is given by the formula. EMF of the cell is given by the formula. E naught of the cell here. Cell consists of two electrodes, remember. That plus 2.303 RT by NF log of concentration of the reactants by concentration of the products. This is the Nernst equation to calculate the EMF of the cell. Now, how do we calculate the E naught of cell? E naught of cell is calculated by the formula E naught of cathode minus E naught of anode. Now, we'll take up an example so that you will understand this better. Now, the question I will write and then we will try to explain. So these all are for 1 mark competitive exam you should do. You cannot take more time. Calculate the EMF of the cell. CR3 plus, the concentration is 1.0 into 10 to the power minus 3 molar, salt bridge, nickel 2 plus, it is also 1.0 into 10 to the power minus 4 moles here, and nickel at 25 degrees Celsius. And they've given if E naught of chromium is minus 0.25 volt and E naught of, this is E naught of chromium is minus 0.74 volt. E naught of nickel is minus 0.25. Now, how do we work this problem? To work this problem, firstly, we will try to understand or calculate E naught of the cell. E naught of the cell will be E naught of cathode minus E naught of anode. Amongst these two, larger value will be cathode and least value will be anode. It's a negative value, remember. So it will be E naught of nickel minus E naught of chromium. That will be equal to minus 0.25 minus of minus 0.74. So that will be equal to 0.49 volt. E naught is 0.49. Now here, the Nernst equation for the cell, it's given. E cell is equal to E naught of cell plus 0.0591. Because the question clearly says 25 degrees Celsius. So R is 8.314, temperature is 298, Faraday is 96,500. So this value becomes 0.059 divided by n log of concentration of the reactants divided by concentration of the no, this is for, yeah, correct. This is products. Now, what is E naught of the cell? We found out E naught of the cell is 0.49. 0.49 plus 0.0591 divided by n. I don't know what is n. So in order to find n, look at this equation. Chromium is undergoing oxidation from Cr to Cr3 plus. Since charge is increasing from 0 to 3 plus, it means it's giving 3 electrons. And you see here, nickel 2 plus to nickel. So nickel 2 plus accepts 2 electrons to give nickel. Now the electrons are not balanced. Here we have 3 electrons, here we have 2 electrons. In order to balance these electrons, multiply the first equation by 2, second equation by 3. 3 2s are 6 and 2 3s are 6. So n becomes 6. This is how you calculate the value of n. And log of 1.0 into 10 to the power minus 4 divided by 1.0 to 10 to the power minus 3. So on substitution and simplification, the answer what we get is 0.42 ohms. So E naught of the cell. This is for a electrochemical cell. This is how we calculate the cell potential or EMF of an electrochemical cell. Now, one more equation I have to give you, then we'll go for other set of problems. Now, how this electrode potential is related to equilibrium constant. So a problem based on this also is important. A relationship I'll give you, and also we'll work one simple problem based on this. So you should be fast enough in calculation, otherwise you will get stuck up. So if you find it difficult to calculate, stop that, go for the other question, finish off the next questions, other questions, and you can come later to solve these questions. Now, coming to the relationship between electrode potential and equilibrium constant, few formulas you have to remember. Right. Now, first formula you have to remember is E naught of cell. Standard electrode potential of the cell is equal to 2.303 RT by NF log of Q. K is called as equilibrium constant. The same formula at 25 degrees Celsius, we can write E naught of cell is 0.0591 divided by M log of K. This is at 25 degrees Celsius. Now, the other form, this is one formula which I want you people to remember, because they can ask you to calculate the equilibrium constant. Standard free energy and electrode potential. Delta G naught is equal to minus MF E naught of cell, standard electrode potential of cell. Now this is equal to, or we can write delta G naught is also equal to minus 2.303 RT log K. Kc otherwise, concentration log Kc. Since left-hand side is same, we can equate the right-hand side. So we can write delta NF minus NF E naught of cell is equal to minus 2.303 RT log Kc. So dividing by NF, dividing by minus NF, we get E naught of cell is equal to 2.303 by NF RT log K. See, this is the formula. This is the formula which I gave here. This is the formula. So based on this formula also, they can be asking you a problem. So you should remember a problem. So you should know how to find the anti-log value here. Because when they ask you to find K, equilibrium constant, and finally the answer will be what? Anti-log you have to find. Now, this relation is also important. Delta G naught is equal to minus NF E naught, or delta G naught is equal to minus 2 point. These are two separate equations. Combination of these two equations are this. So you should remember three equations. That is relation between standard free energy change and electrode potential, standard free energy change and the equilibrium constant, relation between equilibrium constant and electrode potential. Now coming for conductance, conductance is defined as reciprocal of resistance. So unit for conductance is per ohm, because unit for resistance is ohm. Therefore, unit for conductance is per ohm. Now, we have different types of conductance we have to remember. One is specific conductance, molar conductance, and then we have equivalent conductance we don't learn. So specific conductance. The specific conductance is represented by letter kappa. It's not K, it is represented by letter kappa. So specific conductance kappa is given by the formula. It is 1 by R into L by A. So this L by A is called a cell constant. Or maybe we can say resistance is directly proportional to length and inversely proportional to area. This is what it is. So this formula you have to remember to calculate the specific conductance. The unit for specific conductance is per ohm meter square per mole. Per ohm meter square per mole. This is the unit. No, this is the unit. No, this is not the unit for specific conductance. Sorry. Specific conductance unit is no. This is for molar conductance. This unit is for molar conductance. Per ohm is also called as Siemens, right? So here it will be Siemens per meter. So the unit for specific conductance is Siemens per meter. Next, we have molar conductance. This molar conductance is represented by letter lambda m. This lambda m is given by the formula K into V. What is this K into V? K is specific conductance and it's volume of the solution. Or we can write lambda m is equal to K into 1 by C. Because volume is inversely proportional to concentration. Finally, lambda m. This formula is very important to work out the problems. 1000 K by C. So molar conductance can be calculated by the formula 1000 K by C. K is called as specific conductance. K is called as specific conductance. In Bangalore, there is an information. In Karnataka, there is shocking information that the results are coming out tomorrow. That's what the latest government order says. So for 12th standard students in Karnataka, PUC, the results are coming up tomorrow by 11 o'clock on the net. I don't know how many of you are from Karnataka. Anyways, all the best for you. Anybody from Karnataka? All right. Don't panic. If you are in Karnataka, don't panic. Everything will be good. All right. Coming to the next. So this is with respect to specific conductance and molar conductance. A question generally they ask like this: a solution of potassium chloride potassium chloride of concentration 5 into 10 to the power minus 4 mole per decimeter cube has conductivity of 7.4 to 10 to the power minus 5 Simon centimeter inverse per ohm per centimeter. Per ohm is Simon centimeter inverse. So this is the unit for specific conductance. Simon per meter or per Simon per centimeter. Calculate the molar conductance. Calculate the molar conductance. So molar conductance lambda m is calculated by the formula 1000 into kappa divided by concentration. So 1000 specific conductance they've given as 7.4 into 10 to the power minus 5 and divided by concentration. What's the concentration they've given? They've given the concentration as 5 into 10 to the power minus 4. So what happens when we simplify? The answer we get is 148.0 Simon centimeter square per mole. This Simon centimeter square per mole is the unit for molar conductance. Is the unit for molar conductance. All right. Now, the next topic in this chapter, the formula, what you're supposed to remember is based on Cold-Rush's law, the problem based on Cold-Rush's law. So, Cold-Rush's law clearly states that the conductance of a weak electrolyte will be equal to sum of the conductance of all the individual ions. Okay. Now, coming to the Cold-Rush's law. Where is the chart? Cold-Rush's law. Cold-Rush's law states that conductance, molar conductance at infinite dilution is equal to conductance, molar conductance infinite dilution of a cation plus molar conductance of the anion. So sum of the conductance of all the ions will be called as the Cold-Rush's law. Now, one of the example we will try to take and then we'll solve. Before we solve, this is one formula which you have to remember. The second formula which you have to remember is alpha, degree of dissociation is given by the formula lambda Cm, molar conductance at a particular concentration divided by molar conductance at infinite dilution. This is the formula. On simplification, we can calculate the degree of dissociation by the formula C into lambda Cm the whole square divided by lambda naught m into lambda naught m minus lambda C. So this is from lambda naught m is molar conductance at infinite dilution. Lambda Cm is molar conductance of a particular compound at a particular concentration. One problem we will try to solve. Molar conductance. Where is that pen gone? Molar conductance. They've given limiting value in brackets. Limiting values means it is molar conductance at infinite dilution of HCl, NaCl, CH3CONa are 426, 126, and 91 Simon centimeter square per mole. Simon centimeters per mole, square per mole. Calculate lambda naught of acetic acid. They're asking to calculate the lambda naught of acetic acid. So lambda naught of acetic acid is given by the formula. See, as sodium acetate they've given, NaCl they've given, and HCl they've given. So lambda naught of CH3CONa plus lambda naught of HCl minus lambda naught of NaCl. If you observe this Na plus and this Na minus, this is minus and will get cancelled. This H plus and this Cl minus, sorry, and minus Cl minus will also get cancelled. So you should be in a position 91. So that will be equal to 391 Simon centimeter square per mole. So this kind of problems will be asked. And a few of the problems they can ask is, they can ask problems based on Faraday's laws. Give me a moment. Hello. So this is with respect to Kohlrausch's law. And few of the problems we'll have to solve based on Faraday's law. Faraday's first law, second law, and you need to know the chemical reaction on batteries and fuel cell. So if you know these few more concepts and the chapter on electrochemistry, you can solve questions. Faraday's first law, second law problems you can directly go through from your materials. Thank you. We'll stop the class now. Thank you.
Thank you.